All right, let's talk about a few different types of metamorphism that can happen depending on where on Earth's surface the metamorphism is happening, what's causing the pressure and the temperature increase, what sort of plate tectonic setting you're in. Those are all details that will factor into the metamorphic types that we're going to look at. So if you were to look at this block diagram, we've got a couple of things going on. We've got plates moving apart over here. We've got plates pushing together over here and over here in two different ways. We've got what looks like an asteroid or a meteor hitting Earth. Where are some places on here that we could have heat and pressure and hot fluids causing metamorphism of rocks? Think about that for a second. What sorts of places you would expect to find some of this metamorphism happening? Really, anywhere below the very surface is going to have metamorphism, and above the depth at which these rocks melt. So you can see some of these rocks are melting in this subducting slab over here and over here. So this isn't metamorphism. And down in the mantle, it's not metamorphism because we don't have those mantle rocks they've been there the whole time. They're not being subducted. They're not coming from Earth's surface. So there's really no changes in those going on. But anywhere in between, you can have metamorphism, including right underneath that impacting meteor over there. And different types of metamorphism will happen at different spots. Some of them might be called shock metamorphism, where we've got really high pressures from this meteor impacting and sort of moderate temperatures because this is adding some heat to it. But for the most part, a lot of what's causing the metamorphism here is a really fast force that's forcing minerals together at Earth's surface really quickly. We've got something called regional metamorphism, which happens where convergent plate boundaries and sometimes some magma upwelling generates medium to high pressures and medium to high temperatures across a whole range of places, often in mountain belts. We've got high pressure metamorphism happening right where the two plates are converging together. You've got really high forces, high pressures there, but it hasn't subducted far enough that you get really high temperatures. So this is sort of high pressure, but low temperature metamorphism. There's contact metamorphism that happens whenever you've got some magma that's coming up. It's going to heat the rocks right around it, but it's not going to really put any pressure on them. So this is like high temperature, low pressure metamorphism. There's simple burial metamorphism by putting rocks on top of other rocks, even if you were just sedimentary rocks, layering them one on top of another. After you go down a certain depth, you're going to get to low to moderate temperatures and low to moderate pressures. But they aren't directed. Simply by burying rocks, you can get metamorphism to happen. One more that we'll point out is seafloor metamorphism that happens because as plates move apart and you have sort of this open area where magma, where partial melting of the mantle is coming up and generating new igneous rocks, you've also got seawater percolating down through the pores in those rocks, interacting with some of that magma. And then it rises and it carries new elements dissolved in it to the surface. And that metamorphism is largely happening because of those hot fluids carrying different elements and depositing them in different ways. So this is a sort of a subset of different processes that we might call hydrothermal processes. Hydro, H-Y-D-R-O, thermal. Water and heat. So let's break these out and talk about them in a little bit more detail. Regional metamorphism. These are large belts of metamorphism that happen under mountains. And these mountains are happening because of convergent motion. When I say convergent, I mean pushing together. Happens over a large area because these plate boundaries happen over a large area, and it's very high-grade metamorphism. You can find rocks in the Great Smoky Mountains if you're looking in the right places that have some of these regional metamorphic rocks. So some places you can find schist and even gneiss in a few spots that have formed at high temperatures and high directed pressures because the Great Smoky Mountains were part of an old convergent plate boundary. Contact metamorphism, that's places localized to where older rocks contact new igneous rocks and or magma. And since they're in contact with that really hot magma, it must be high temperature, but the magma being there doesn't add any pressure on those rocks. So it's relatively low pressure. Would you get foliation in contact metamorphic rocks? No. That's because there's no extra directed pressure exerted by that magma. So we're not thinking about foliation in those places. One good example where you can find really good regional metamorphism is if you look up in New England, a lot of those rocks have been metamorphosed. And that's because of an ancient collision that happened. Sort of, you know, if we drew the axis of that collision, it might be like approximately right there is the center of it. The very highest grade rocks are there. And as you move away from it, you'll find lower and lower grade rocks. Low grade to high grade. As you were nearer to the collision zone, you had higher temperatures and higher pressures metamorphosing those. And so we have chlorite minerals on the outside, and then biotite, and garnet and staurolite, meaning you're an intermediate grade. Remember, we can use the minerals to tell us what the grade of metamorphism was. And in the very center, we have high grade metamorphism. You see that on this side, but what happened to the rocks over here? Why don't you see a lot of biotite and then chlorite out over here? What happened to those rocks? Turns out that those rocks, the rocks that have this biotite and chlorite, have been separated. Plate tectonics has split those apart and moved those rocks. And now they're part of Ireland, Scotland, Scandinavia. Because plate tectonics over time has split those rocks and moved them elsewhere. So contact metamorphism, for example, here, we have, this looks like it's roughly parallel to the sedimentary rocks that it's around. And this is igneous rock, an igneous intrusion. If it's parallel to the layers, it's called a sill, right? And so this sill has baked the rocks around it. And so these have been subjected to contact metamorphism, really just a way of saying that the old rock that's here gets baked, but no pressure has been exerted on it, no new pressure anyway. To give you an idea of sort of what characteristics those rocks have from contact metamorphism, you could start with some unmetamorphosed sediment. You think of something like clay as being unmetamorphosed. If you apply just a little bit of heat to it, you'll get something more like brick. And if you heat it up even more, you would get something more akin to pottery. And if you heat it up even more than that, you would actually get something like porcelain. Those are sort of man-made equivalents to unmetamorphosed sediment, and then low grade, intermediate grade, and high grade hornfels. None of these are foliated. We don't talk about them a ton other than to say that it's a non-foliated rock. Talk about some other types of metamorphism. Burial metamorphism occurs over large areas that have simply been buried by new sediments, typically a low-grade metamorphism. And our part of East Tennessee has some of these, a little bit of slate, a little bit of quartzite, a little bit of marble from this low-grade metamorphism. There's also shock metamorphism that happens very rarely, really only as a result of meteor impacts. But some places we can still find evidence of these that happened hundreds of millions of years ago. In fact, there's one in central Tennessee where we can find some shock metamorphosed minerals formed under low temperature but very high pressure from the impact of that meteor. Then these hydrothermal alterations that I talked about, they can also be described by a word called metasomatism. So if you see that, these words I'm going to use pretty interchangeably. These are special because they involve chemical reactions with hot fluids and then the dissolved chemicals that they carry. hydrothermal processes or metasomatic processes are the source of a lot of different ore deposits. And because those carry weird elements that don't really like to sit around in igneous rocks, like copper and silver and gold, like sulfide minerals, like different heavy metals. And so these ores often form as a result of hydrothermal processes. We looked at how they can form at divergent boundaries at the seafloor, but they also happen in any other places where water can circulate near magma. So like hot springs, that means that you've got water percolating down, getting heated by the interior heat of Earth or even magma nearby. Yellowstone is a really good example. You've got hydrothermal processes going on in all these types of locations. Where plates are separating at a divergent boundary, and you've got partial melting of the magma or of the mantle down here, producing magma. We've seen that before. And that magma can rise. Now it's adding heat to this area near a mid-ocean ridge. And in these places, ocean water can percolate down through that basalt or the gabbro that's forming at these places. And it interacts with the heat here. It dissolves certain minerals, it precipitates other minerals, and it alters that basalt and creates a rock that we call a serpentinite, where we take the olivine in that rock, that green mineral, and we turn it into weird different minerals by hydrating it. Just a view of what a serpentinite looks like. We've taken some of those green minerals and we've altered them. We've filled in some of the gaps that have formed in this rock with calcium carbonate, but they tend to look kind of weird. They'll still look mafic, but they'll look very different than some of the other rocks that we have because they contain very different minerals that have been affected by hydrothermal activity. I had mentioned that a lot of ore minerals form from metasomatism, and we've looked at two earlier on when we were looking at the minerals in this class. We looked at galena, which was the purplish lead sulfide mineral. We've also seen pyrite, right? Both of those are metasomatic minerals, minerals that form from hydrothermal activity. Because water at really high temperatures can dissolve both lead and sulfur and leave them behind in certain spots. They concentrate them and leave them behind in gaps in rocks. Looking at this, I can't necessarily tell whether that's pyrite or gold. But metasomatism can also create deposits of valuable minerals like gold and silver, because those really only dissolve under really high temperature conditions, and then they can be left behind in gaps in rock like this.